Assalamu alaikum. It's our 15th lecture of Advanced Electromagnetic Field and Waves, and in this lecture we are going to discuss about the waveguides and resonant cavities. Okay, so what are basically the waveguides? Waveguides are basically the guiding structures. Okay, as you can see different diagrams like this, you can easily see that this is your rectangular coordinate and wave is going inside, and this is your cylindrical wave is traveling inside. This is your triangular type coordinate and wave is traveling. There is also another type of coordinate which is the t shaped, which in which electric field are going to move. So basically wave guides are basically the guiding structures, you can say in simple words. Okay, so there are many types of guiding structures. Okay, like mostly used are this rectangular type and this cylindrical type shapes. This cylindrical type shapes waveguides, you know that basically used in a very good application is that the optical fiber. You know that this cylindrical type waveguide is used in the optical fiber for the communication system, for the transfer of a light from one place to another. Okay, so what is basically the microwaves? Microwaves, you know that have a basically the frequency of 300 megahertz to 3 gigahertz, very high frequency. Because the frequency of microwave is very high, so the wavelength of the microwave is very short. As you know that there is an inverse relationship between the frequency and the wavelength. Whereas your microwave is concerned, the frequency is very high. As the frequency is high, so definitely wavelength is very short. So in microwaves, we are going to use metallic waveguides. Okay, this is like metallic waveguide. So in microwaves, we are going to use only metallic waveguides, not cylindrical, not triangular, not T-shaped. Why we only used metallic waveguides in microwaves? Because you know that in metals, microwaves are not going to penetrate. There is less amount of energy used, energy loss. So basically what's our work of using these waveguides are? We are using these waveguides to minimize the loss of energy, because loss of energy means loss of signals. Loss of signal means there is minimum loss of electric and magnetic field, because these are electric and magnetic fields which are going to transfer the energy, which are basically transferring the data from one place to another. These are basically the field waves in which all the data is concerned. So if there is some loss in that fields, so definitely there is loss in data. So we are going to minimize our loss. Okay, so we can minimize our loss by using metal waveguides when we are using microwaves, because the microwaves are high frequency. So that's why we are using metallic waveguides. Okay, because in metals microwaves not penetrate. So you are using so there is less amount of energy loss, means less amount of field waves and less amounts of field loss. There is suppose this is your metal waveguide. Your electrical magnetic field is going, strikes the one boundary, again strikes the other, move inside. There is less amount of energy loss, that the less chances, less probability that the wave penetrates that metal. Okay, and that's why whenever we are dealing with the microwave, we are using the metal waveguides. Now what is metallic hollow cylinder? This is like you can see metallic hollow cylinder. Okay, this is hollow inside. There is nothing inside. Inside is only there is field wave has to travel. So signal, how signals now travel? Signals can travel in three modes. The name of three modes are TEM, which is transverse electromagnetic, TM, transverse magnetic mode, and TE, which is the transverse electric mode. In TEM, your electric field as well as your magnetic field are transverse, while in TM mode, your only magnetic field transverse. In electric transverse electric mode, your electric field is transverse. So let's take an example for TEM, means your electric field as well as your magnetic field are transverse. So you can see this is your wave propagation. Your electric field and magnetic field is are perpendicular to each other. Your wave is traveling inside. Okay, so this is basically the electric and you can say that the electric as well as the magnetic field are transverse. Let's take an example for the case of TM mode. So how you can propagate like TM mode, because if you propagate same, so electric field and magnetic field are again transverse. So to only set your, for the case of TM, to only set your magnetic field as transverse, you can adjust like this type, like you are using this cylindrical hollow, and you are propagating your electric field in this direction and this. So you can see this is your electric field direction now changes, and this is your direction of wave propagation. So in this scenario, and this is the z-axis, so in this scenario you can say that you can make the components of electric field uh, by increasing those abstract lines. Okay, so you can easily see that in this TM mode your magnetic field is transverse, okay, while your electric field has making components with the z-axis, okay, in hollow. So TEM mode not exist in hollow, okay, only TM mode exist in hollow. Why TEM not exist in hollow? Because in hollow there is no electric fields, and there is no not some medium inside, that is totally empty from inside. And the another concept is that there is no field inside this hollow. That's why TEM mode is not exist in the hollow, only TM mode, okay, in which the magnetic field are transverse. As you can see, the frequency is very high for the case of microwaves. So as you are increasing the frequency, Kirchhoff's law fails. Okay, Kirchhoff's law only applicable at low frequencies. Whenever you are going to increase the amount of energy, Kirchhoff's law fails. Okay, so what are now to solve these equations? As we know that the source free time harmonic equations of this Faraday's law, del cross E, which is equals to iota omega mu h, and you also know that the Ampere Maxwell's law, del cross h, which is equals to minus iota omega epsilon E. Okay, and you know that their final solutions results of these equations are del square E plus k square E equals to 0. Similarly, for the case of magnetic fields, del square E plus k square h, del square h plus k square h equals to 0. Okay, so these are the Maxwell's equations of electric and magnetic field, divergence of curl of magnetic field and curl of electric field. Okay, now what we are going to solve, we are solving one component, like we are solving z component, and finding z component, then we use some formulas to find y and x component also. Why only z components we are finding? Because the z component is common in Cartesian as well as the cylindrical coordinate system. That's why we are taking only z component of electric field and z component of magnetic field. And then after finding the z component, we are using some formulas to find the x as well as the y component. Then we can easily uh, uh, find the comparisons. Okay, so how we can find that? First of all, let's just take the curl of electric field, which is equals to iota omega mu h. We already know that the Faraday's law. Okay, we already, this is this in previous videos. So we have to take the curl of electric field means del cross E. So this is del cross E, x y z, partial by partial x, partial by partial partial z. Del cross E means ex ey ez. You have to take the determinant iota omega mu as it is, and x, which is this. Okay, so after taking determinant, what you have to do, you have to just take common. Okay, common of x coordinates, common of y, common of z equals to this. So here is what iota omega mu hy. So iota omega mu hx equals to determinant of this, which is common, which is this. Similarly, iota omega mu hz equals to this, and iota omega mu hy equals to this. Just take common, multiply determinant, and take common from these two. Okay, you can easily find here. Okay, just what you have to do, you just have to take determinant of this, and after taking determinant, this is x direction, here is also x, so hx becomes equals to this, hy becomes equals to this, and hz equals to this, and there is a factor this also with h. Okay, so these are your final results. Basically, what's our task is, we are finding our ex in term of ez and hz, and we are also finding ey in term of ez and hz. Similarly, hx in term of ez and hz, and similarly we can find hy in term of ez and hz. And these are our final equations we already find previous. But the thing is that because the wave propagation is in the z direction, so partial by partial z, whenever there is partial by partial z, it becomes iota k. Okay, so here you can see, here is the partial z, it becomes iota k, here is also it becomes iota k. So these are your first three equations. Similarly, you have to do for the second, for Ampere's Maxwell's law, which is the divergence of magnetic field equals to minus iota omega summation E. So just take the curl and this, multiply, take determinant similarly as you did before, and you have to take common from this. So ex becomes equal to this, ey becomes equal to this, and ez equals to becomes equal to this, and there is a factor of minus iota omega epsilon with e values. Okay, you can see here. Similarly, partial by partial z again becomes equals to iota k. So again this similar equals to this. Now you can name these equations as equation 4, 5 and 6. Now these are your first three equations, and these are your next three equations. Now as I told you, our task is to find the value of ex, ey, hx and hy in term of ez and hz. So how we can do this? As we want ex, first of all we want ex in term of ez and hz. As we want ex in ez and hz, so from that, putting the value of hy from equation 2, so we are using to solve hy. So to solve equation 2 for hy means find the value of hy. You can find easily hy, that divide iota omega mu to the other side, you can get the value of hy. So after finding the value of hy from equation 2, put that value in equation number 4. This is your equation number 4. Here you have to put the value of hy. Okay, so here you can see I find the value of hy. So this, when this iota comes upside, it becomes minus iota, and minus minus become plus iota. Okay, and this is the value of hy. Now I have to put this value of hy in equation 4. Here is the hy. Okay, so you can put the value of hy easily. You can see partial by partial z is as it is, iota. Similarly, this is my equation 4. We have to put the value of hy. This is the value of hy. Now simply you have to substitute your values, multiply this with this, multiply this with this, you will get this. And because we need the value of ex in term of ez and hz, so move ex terms on one side and ez and hz to the other side. You can see ez and hz to the other side, and ex term here, take ex common, and you have to take LCM, divide and multiply this terms other side oppositely, so this, and multiply this with this and this with this. You can easily get the expression of electric field ex component in term of Ez and Hz. So that's all for this lecture number 15 of advanced electromagnetic field and waves. In this, we will just overview about the resonant and cavities. Thanks for watching. Till then, Allah Hafiz.